This lesson is for Chapter 3, Section 2, Polynomial Functions of Higher Degree. Guys, go ahead and open up your textbooks to page 252, get out your notebooks, and we'll start. All right, polynomial functions. With a polynomial function, you're going to have a continuous graph, so there will be no breaks in the curve when we graph. And it's also going to have smooth and rounded curves, no jagged edges like a absolute value function would have. That would not be considered a polynomial function. The easiest polynomial graphs that we're going to be taking a look at are the ones that are in the form f of x equals x to the n, where n is an integer greater than 0. So in other words, we're going to be looking at things that look like parabolas. There'll be higher powers than a power of 2 even, and we'll be kind of taking a look at what the tendencies of that are, and see what that does to the graphs of them. Remembering, oh gosh, is that section 1? No, chapter 2, the shifting. You're going to see a lot of those shift and shrink and stretch kinds of things happening to these functions of this form, but the good thing is you guys were really good at those last chapter, so hopefully you remember them for this. Now, a few extra things, and this is going to take some decent note-taking to get this down. If n is even, in other words, if the power of x is even, say x to the second power, x to the fourth, etc., the graph is going to resemble the parent function f of x equals x squared. So they will look parabola-ish. If n is odd, okay, so if you have an odd power, a 3, a 5, a 7 on your x, it's going to resemble the parent function of x cubed. So this parent function, we all remember, looked like a parabola. The parent function of x cubed, remember, was that little kind of curvy one. So if we were going to sketch these, now these are going to be really rough sketches. Try to keep in mind what did stuff look like when we shifted them. So letter A has an x plus 5 inside. That still means what it did before. If you add 5 to the x, rather than at the end, that plus 5 is a left shift of 5. It is an even power. My pens are off again. Hang on, guys. It's an even power, so that means it's going to resemble a parabola. So again, we're not going to be looking for anything with this graph that's super exact, but we're going to give an approximate look to the graph. So that left shift of 5 and parabola-ish looking, it's going to be a little fatter when that power increases. Okay, it kind of flattens out here. But that's the general gist of what letter A would look like. Okay, so we're going to get rid of that one. Let's take a look at B. We have x to the fourth minus 7. Now recall what the minus 7 at the end of it means. That means we're going to do a vertical drop of negative 7. X to the fourth again has an even power. So again, it's going to resemble a parabola, just going to kind of flatten and wide down there at the bottom and look something close to this. Okay, get rid of that one, go on to C. 7 minus x to the fourth. Now I'm going to rewrite that one because that confused a few of you last chapter, that when the 7 was up front, you didn't quite know what to do with it. That plus 7 is a positive shift, and then the negative in front of the x to the fourth, remember, means reflecting. So if we're going up 7, but the reflection tells us instead of opening up, it's going to open down. Okay, so that's roughly what letter C would end up looking like. And the last one there, you have that 1/4 out in front of our function. This one again is going to be to the 4th power. It's kind of funny that in the checkpoint here for number 1 they gave us all even powers of x, so they all resembled parabolas. But we do have a couple of things going on with this one. We have a -3 shift, so we're going to be going to the right. And then the 1/4 out front is going to make it do a vertical shrink. So it's yet, but still resemble a parabola. So I think you flatten kind of fat out like that. Okay. Now, when we're trying to figure out these tendencies a little bit more accurately, we can do something that's called the leading coefficient test. The degree of the polynomial. The degree, remember, we had a lesson or two ago, or it must have been yesterday. The degree of the polynomial is the highest exponent that's in the function. All right, so if the degree of the polynomial is odd, so the highest exponent is odd, a positive lead coefficient will have a graph that's going to fall to the left and rise to the right. It would look, and think, one odd power could possibly be x to the 3rd, and we already know that that function falls to the left and rises to the right. 2, if a negative lead coefficient is there, now you're going to have a graph that's going to rise to the left and fall to the right. Well, that negative out front would be like the reflection spot. So, if you think about these logically, we already knew this. So our number 1 and 2 are related based on information that we learned in chapter 2. Okay, so a positive lead coefficient is going to have a graph that's going to fall to the left and rise to the right. One example could possibly have been, f of x equals x to the 3rd. We have odd power, positive lead. We know what that parent function looks like already. If we have a negative lead coefficient, maybe -1, even simple like that, with that, we know what that does. That's going to do the reflection. So our picture is going to do this instead. And if you look at it and break it down, it rises to the left and it falls to the right. Okay, so don't get caught up too much in having to memorize. You do, but you don't. So if you pick it apart and use our chapter 2 information, you could end up figuring it out even if you'd forgotten some stuff. If the degree is even, all right, so if our highest exponent is even and has a positive lead coefficient, it's going to have a graph that rises to the left and also rises to the right. Well, let me give you another example. Positive lead, even degree. Well, think about your parabola and what it does. Doesn't it rise to the left and rise to the right? Okay, so that would be the tendency for anything. Not necessarily just the 2nd power, but the 4th, and so on and so on, as long as it's even. Now the negative lead coefficient on that's going to fall to the left and fall to the right. Well, take that same possibility there and put a negative in front of our x squared. Again, from last chapter, we know what that's going to do. It's going to reflect that parabola. So you can see how that graph is going to fall to the left and fall to the right instead. Okay, so again, all of these things, it seems like it's a lot that you're going to be expected to remember, but you don't. You can go back on what we knew from chapter 2 and apply it. So let's take a look at these couple of things and describe the right and left behaviors that we see. All right, so first thing, our highest degree is 3. That's odd. Our lead coefficient is positive. All right, so when your lead coefficient was positive and your degree is odd, remember how it took on a similarity to that parent function? So it falls to the left and rises to the right. Okay, so that's not so bad, right? Take a look at the second one. Again, we have an odd degree, but we also have a negative lead. Okay, so instead of what we had up above, aren't we going to get the reflection of it then? Or something, a reflection of that kind of a curve anyway. So instead, it's going to be more like this. So describe that left to right behavior. It's going to rise to the left side. Whoops. And fall to the right. Okay, so describing the left-right behavior, that's all it is. You're putting into words what that graph is going to tend to do. Real zeros of a polynomial function. Okay, so this is something else that we're going to be looking to find. Real zeros, remember, those zeros are found as the x-intercepts. So step number one up here, or piece number one says if a polynomial has a degree n, it's going to have its real zeros. Number two, the graph of that function will have at most n minus 1 turning points, or maximas or minimas. So if you've got a degree of 3, then you're going to have 2 points where the graph changes directions. Okay, so those turning points are where, you know, instead of going up, it starts coming down, or where it was kind of decreasing, it all of a sudden starts increasing. Those are turning points. So the number of turning points is always going to be 1 less than the degree of the polynomial. So find all the real zeros of f of x equals 12x squared minus 36x. This one's checkpoint problem number 3. Oh, I didn't write the page number on that one. What page number was that? Checkpoint number 3 must be 256. Okay, so if we're taking a look at this one, if we want all real zeros, one way that we found zeros was factoring. Okay, so if I look at this one, I have no coefficient on my x to the third power, so I can't pull a number out of all 3 of those, but they do all have, an x in common, so I can take that off. X squared minus 12x plus 36 is what I'm left with inside. Now this is looking like something more that we can break down. If you look at the 36 and see that we need a negative 12 inside, this is a factorable polynomial. If we go negative 6 and negative 6, we'll get that negative 12 in the middle that we need and a positive 36 at the end. Okay, so when we're looking for our zeros then, out front, that first term, the only thing to make that 0 is a 0 itself. The next term, a 6, as well as the last one because they're kind of a duplicate factor. Okay, now the degree of this polynomial was 3, right? So how many turning points would there be? N minus 1, we take 1 away, we're going to have 2 turning points. Okay, so that means it's going to loop twice, change directions. Repeated zeros. Okay, this is at the very bottom, moving towards the bottom of page 256. If a factor, x minus a to a power, okay, so you're going to have x minus some number raised to a power of a polynomial, has a power which is greater than 1. So if it's a squared power of k, or if it's cubed, you're going to have repeated zeros. Now that makes sense if you think about it. Like on our last example, remember how we had an x minus 6 and an x minus 6? We're going to have 2 zeros at 6. Okay, so because that came or could have been written x minus 6 squared, okay, anytime you have a greater power to that factor than 1, so for example a 2 or 3, you're going to have this repeated 0 thing going on. Okay, now here's a couple of things for you to make note of. If k, if that power is odd, the graph is going to cross the x-axis at A. Okay, so if the power is odd, the graph is going to cut through the x-axis at whatever that number was. If k is even, the graph is going to touch the x-axis at that digit. Okay, now the main thing that this is important to remember it for, it's, you know, you could always pick the points, stick them in, and you can find it out yourself. But if you remember it, making that rough sketch is just going to go a lot faster. All right, so these this information here is something that you could probably, you know, not forget, but not worry about too much as a memory thing, because you could always plug those 6's in and you could figure out where it's going to take you. All right, standard form of a polynomial. When we write a polynomial in standard form, we rewrite it or reorganize it so that the exponents are in descending order. Okay, generally when you leave an answer or finish a problem, this is how you want your numbers or your terms to be written, is in descending order of exponents. Let's take a look at sketching this graph. Okay, so figure out first, what are the tendencies of it going to be? Well, so the first thing I'm going to look at is degree. Okay, the degree of this thing is a 3, which is odd. Okay, that tells me something. The lead coefficient. The lead coefficient is 2, and it's positive. That tells me something. Okay, so between having an odd degree and a positive lead, I know that this thing is going to fall to the left and rise to the right. Okay, so that's back on our other thing. Now we need to find our zeros. Okay, so looking at 2x cubed minus 6x squared, I notice that I can take a 2 out, and I can also take out x squared. So that leaves me with x minus 3. So what 0 would there be for this front term? 0 itself. The only thing to plug in there to get 0 out of that front term, 2x squared, is a 0. My second factor, or my second piece, my 0 there is a 3. So those zeros, or those x-intercepts, are going to be where my curve ends up passing through or touching the x-axis. So I know those points, 0, 0, and 3, 0, are going to be part of my graph. Now, a couple of extra random points are going to help me out, but I know that this graph is going to tend to make that shape. So I want to pick a couple points maybe to the left of it, in between them, and a point to the right of it, so I can get an idea of where this all is going to go. So how about if we were to pick a -2 and plug that in? Okay, -2 put in, is going to be -8 times 2 and -6 times 4, which is -24. That's really going to be down here, way down here. So keep that thought in mind. How about a -1? Okay, so 2 times -1 cubed minus 6 times -1 squared. We're going to get a -2 minus 6, or -8. Okay, so that one comes onto our graph. In between 0 and 3, I'm going to pick a point. So I'm just going to put in a 1. Where's my graph going to take me at 1? So 2 times 1 cubed minus 6. So this is going to give me 2 minus 6, or -4. So 1, -4 is a point. And then let's pick one that's on the outside. Let's go with 4. So 2 times 4 cubed. Well, 4 cubed is that 64, times 2 is 128. And then 6 times 16 is 96. So that one's going to be roughly 32. So again, it's going to take off and end up way up here in the boonies. So now let's try to put all this together and get that shape of a graph that we know we kind of want. We want to go up, and then we want to go down, and we want to go up so it kind of resembles our parent function. Remembering that we have to have 2 turning points if our degree is 3. So we know it's going to take those couple of dips. When you go up, it's going to start coming down. When you go down, it's going to start coming up. And it's going to look something like that. All right, sketching this one. Okay, with this one, I decided to go ahead and do this one as well because it was a weird one that had fraction stuff in it. Now, each one of these terms I could clear. And so I chose to do that. I chose to take my equation and send something through it to clear off all of those denominators. So I took the whole thing and I multiplied by 4. Okay, so my front ended up being negative x to the 4th plus 6x to the 3rd minus 9x squared. I just like that a whole lot better. Then I decided to factor out negative x squared. Each term had x squared, and I decided I didn't want the negative attached to my front term, so I took that with it. So now I'm left with x squared minus 6x plus 9, which I can break down more. And now I can find I have a 0 at 0, I have a 0 at 3, and again it's going to be that repeated 0 at another 3. Taking a look at my tendencies, okay, back to focusing on this line. I have an even degree, and I have a negative lead. So an even degree and a negative lead, it's going to be an upside downish parabola-y thingish. But with a degree of 4, I have 3 turning points, right? So it can't just go up and down. It's going to have to go up and down and up and down. Okay, see how it has 1, 2, 3 turning points in that one? So when we try to sketch, that's what we take into account. So we know we're going to come through 0, and we know we're going to hit at 3. Okay, those are our x-intercepts. Those are our zeros that we found. So if we've got to go down to the left and up somewhere here, we're going to bend again and go down again. Okay, a couple of middle points probably would help out because I don't think I did that real great. So let's not skip our middle points. Let's see exactly where we're going to end up dipping into in the middle. All right, so 0, we'll put 3 back on there. Let's figure out where the 2 is. So if we put in x is equal to 2, okay, you'll have negative 2 to the 4th plus 6 times 2 to the 3rd minus 9 times 2 squared. So negative of 2 to the 4th is negative 16. 6 times 8, 48. And then minus 9 times 4, which is minus 36. All right, so that's looking like negative 4. So at here we're at 0, here we're at 0. Looks like at 2 we're at 1, 2, 3, 4-ish. All right, so we can get a little bit better idea of how our curve's going to go. So we're going to go here, zoop down and grab here, then come back here and then again. Okay, so stay on those zeros and then it's going to drop down. Okay. This last piece, intermediate value theorem. We're not going to do a whole lot with this one other than talk about it. What it says is if you locate 2 x values where one has a positive f of x or y and the other one has a negative one, there must be a 0 between them. Okay, so let's just give you a visual. Let's say that at this x value we were up here. But then over maybe at this x value we were down here. Does it make sense that this function has to pass through here and cross our x-axis somewhere? Okay, that's what this is telling you. That if you've got one x value that has a positive y and you have another x value that has a negative y, there's a 0 in there somewhere. There's going to be a spot where you have to hit that x-axis. All right, Page 261 is where your assignment starts. If you go looking through that, you're going to notice there's a nice number of chunks of problems for each of these kinds of skills. Don't be lazy. Do 3, 4 of them out of every section and get really comfortable with this thought and with this process. Again, if you really look and make the connection, there's a lot of overlap between our last chapter and this section. So hopefully that will make it a little bit easier for you. If you've got any questions, that's what we need to deal with in class tomorrow.